I can see it, so it's good.
Great, there we are. So hi everyone, thanks for coming. I just finished my PhD at the University of Oxford, which is how I met Katja, because she was one of my examiners, and she was so kind to invite me to give a talk here on my topic. I've since moved on to Bristol as a postdoc, but I'm still working on the same topic, which is higher order constrained horn clauses. Right, so why bother with higher order constrained horn clauses? It's a fairly recent approach to higher order program verification, which is our main motivation. And in particular, it has been proposed as a unifying framework for higher order verification, similar to how first order CHC is sort of a unifying framework for first order verification. Because existing approaches to higher order verification, such as higher order model checking, refinement types, have their limitations, but in very different ways as well. There seems to sort of be lacking an understanding of how these approaches relate to each other and how to talk about them in a shared vocabulary. For instance, higher order model checking, it's great, it sounds incomplete, can be easily automated, but only for programs with data types that have a finite number of inhabitants. So even for integers, it would require significant extensions. Refinement types, on the other hand, are just incomplete in general. Even some programs with finite data types cannot be model checked using refinement types. And of course, another advantage of higher order constrained horn clauses is the modularity. Because we can incorporate any first order background theory, we can offload some part of the task to this constraint solver, Z3 or some other efficient solver. Right, so the adequacy for higher order program verification relies on a few things. The first of which is expressivity. Can we actually express these problems that we're interested in this language? Can we actually do the same kind of model checking we can do with the established approaches to higher order verification? And the second is solution methods. It's great to have a theoretical framework, but if we have no way of using it in practice, then still no use. And this is joint work with Stephen Ramsey and Eddie Jones in Bristol, and Luke Ong, Toby Cathcart-Byrne, Long Pham, and Dominic Wagner in Oxford. This is just a short overview of my talk. I'll give you an introduction into HoCHC, focusing on some of the semantic intricacies. I'll give you an overview of the project, and then dive deeper into one avenue we've taken, which I'll explain in detail later. Right, so what is HoCHC? Higher order constrained horn clauses. It's a fragment of higher order logic with constraints from a first order background theory. So this logic is higher order because we allow higher order predicates and higher order quantification up to any order, whichever the problem requires. They are horn clauses, so it's essentially a positive existential fragment of higher order logic. And these constraints are drawn from some first order background theory, which can be any first order theory, as long as it's fixed for this particular problem we're interested in. And yeah, this fragment has surprisingly convenient algorithmic properties in that it's semi-decidable, whether some set of HoCHC clauses is decidable or not. No, sorry, solvable or not, which is satisfiable or not, but only given a semi-decidable background theory. So of course, if your background theory is already undecidable, then there's no hope for higher order constrained horn clauses either. This is just an example of a set of HoCHC clauses. It is a set of clauses over linear integer arithmetic. So here, for instance, z equals x plus y is just a constraint, a formula drawn from the first order background theory. Here on the right hand side, we have a head add, which is just first order, so nothing interesting there. But eta is actually a higher order predicate because it takes an argument f, which is itself first order. So we have set of definite clauses and a goal clause. Still very similar to first order Horn clauses. Usually we'll present it in a slightly different way. Instead of having definite clauses and a goal clause, we'll have definitions of the predicates. So this here is definitional equality. It's equivalent. So we have here a disjunction to account for the separate clauses that belong to eta, and we have lambdas at the front of the clauses to account for the arguments. Oh yeah, I'll explain in a bit why this is useful for us, but it's entirely equivalent. So a high order constrained Horn clause problem is a pair of a program, logic program, which are the definite clauses and the goal clause, over some shared set of relational variables. This is the syntax of the goal clauses. So we have constraints from the first order background theory, just a predicate, a variable, of course, disjunction, conjunction, existential quantification, application, lambda abstraction. So if we go back to the clauses here, every right-hand side of the definitions of the definite clauses is itself a goal clause. So really, the definition of the goal clause is all we need to define the entire fragment. And yes, we assume we have some first order background theory with some fixed model that we're considering. So for linear integer arithmetic, it's just a standard model we're considering. So yeah, here you see again that it's just a positive existential fragment. So we have no universal quantification and no negation and no implication to make sure we're sort of monotone. Right, so given a HoCHC problem, we define a model as evaluation that's just a fixed point of the one-step consequence operator we have here. And a problem is solvable just if there exists evaluation that models the program and refutes the goal clause for the standard model of the background theory. For most of this talk, I'll be talking about just this definition of the problem, which is inductive, but you might want to know that there's also a co-inductive counterpart of this, which is very similar, except that we consider a program solvable just if there exists evaluation that models the program and satisfies the goal clause. Right, so I've shown you a bit, evaluation is some assignment to the relational variables, but we have to formally define our semantics as well, of course. The first thing that's important to note is that our semantics is extensional. So this also sets the work apart from work by Dale Miller, for instance, on lambda prologue, Highorder prologue, because that's usually intentional. So consider the simple prologue program, for instance. We have a fact RP and two relational variables P and Q that are essentially equivalent because they hold only if the other one holds. So does RQ hold? Well, yes, in extensional semantics it does. It does not in intentional semantics, because intentional semantics builds the semantics as a sort of term model. So in this case, we see that yes, RP is in the model, but RQ is not in the model. Therefore, RQ does not hold. But in extensional semantics, our semantics is defined by just any function space, regardless of the actual terms occurring in the program. So for us, in extensional semantics, P and Q identify the exact same set of elements. Therefore, they are indistinguishable, and therefore RQ holds as well. So we have these simple sorts, which is just any sort. Sigma is, as source is a type, by the way, just to distinguish them from refinement types, etc. We have an individual sort, which can be anything, an integer, a list, a tree, whatever you're interested in your theory. We have a Boolean sort O of propositions, just true and false, where false is smaller than true. And we have an error type. And these are interpreted as follows. The individuals are just interpreted as any set. So they're not, individuals are not ordered themselves. So even if we're considering integers, then 4 is no larger than 3, because they're just discretely ordered. Propositions are, as I mentioned, just true and false, with true larger than false. And the error types are interpreted as a function space between the respective posets. So it's worth saying that both the Booleans and error types are complete lattices. So there's a total order on the elements. And yeah, here you see again the extensional semantic. Our semantic domains are fixed based on not on the terms occurring in the program. And we're particularly interested in relational sorts, which are the ones that have the Boolean sort of propositions in tail position, and hereditarily so, because these are the variables occurring in our program. Right, so does HoCHC have a least model property? Because of course, if you want to achieve some sort of semi-decidability of the problem, you do need to be able to inspect all the candidates you're interested in. So yeah, does there exist a least model for HoCHC? One that can be found in countable time, hopefully, finite time anyway. Not under the standard semantics, no. So let's look at an example. We have a very simple logic program with the head is px, which is defined by x applied to q, where x is universally quantified, just a free variable, and p and q are predicates from the program. We have these sorts, where we have individual sort 1, which is literally just inhabited by a single element, and O of propositions. So if we interpreted 1 just as a single element star, then the next level up, 1 to O, consists of 2 elements. The element that maps star to 0 and the element that maps star to 1, where the latter is strictly larger than the former. Because remember, we have an order on 0 and 1, which we can raise pointwise to high order sorts. And yeah, we can raise this another level. So this first element here maps this first element here to 0 and the other element to 0 as well. But here we can see that x, which is of the sort 1 to O, could in fact be antitone. And if x is antitone, then q occurs negatively here, which means that if q becomes larger, p becomes smaller. So this is not monotone in general, a logic program of HoCHC. But of course, we can come up with monotone semantics to work around this, which is exactly what we do. We interpreted the individuals in the same way, the Booleans in the same way, but now our function space considers only the monotone elements of this function space. So the ones that preserve the order, like this. If x1 is smaller than x2, then f1 should be smaller than, f of x1 should be smaller than f of x2, if f is in fact monotone. So yes, the monotone interpretation does have a least model property. So it's interesting that on the one hand, we have gotten rid of negation, implication, etc. Everything that seems non-monotone. But somehow in the higher order case, that's not enough to guarantee monotonicity. we do need an explicitly monotone semantics to achieve this. It's something that I don't think arises in the first order case at all. So is then this monotone semantics a natural setting for high order verification? Perhaps not quite yet. So for first order Hom clauses, if you have a monotone interpretation, then this is necessarily continuous as well. Which means that the least upper bounds of directed sets which are going somewhere, in which all two elements share an upper bound, is preserved by the one-step consequence operator. But for higher order Hom clauses, this is not necessarily the case. There do exist examples of the one-step consequence operator in a monotone setting not being continuous. And I'll work through an example in a bit. But the consequence of this is that the least model may not be found in countable time, which is why it's not great for high order verification again. So let's look at the example. We have a relational sorting of foo and bar over a set of individuals interpreted as the natural numbers, extended with some largest element infinity. And we're interested in an interpretation of foo that is not continuous. So first, we define a family of functions, fi, that maps everything that's smaller than I to 0, and everything that's larger or equal to 1. Which gives us an ordering like this. So here you can see on the left, we have the function. At the top, we have the argument it takes. So of course, this order over here, with f0 being largest, f infinity plus 1 being smallest, becomes apparent if you look at the table. Because remember, the order on high order sorts is pointwise. So we say that fi is greater than fj, if and only if fi applied to some x is greater than fj applied to the same x for all x. Right, so we have this order on the f's, which we can then raise to a higher sort by defining this family of functions G. Yeah, the exact definition is not that important. It's a bit more complicated than the f's, because now we also have functions that are not strictly relevant for our definition, but we still need to define them, of course. But the important bits are that we again have an order on all the g's, and that g infinity minus 1 is in fact the least upper bound of gi for all natural numbers I. So here we have again a table. On the left-hand side, we have the g's we've defined. At the top, we have the f's we have defined before. So yeah, as you can see, g minus 1 is the least upper of all the smaller g's. Because yeah, for every natural number I, there will exist a gi for which this value is 1, and therefore gi minus 1 also has a 1 over there. Right, so if we now consider this function h that maps g infinity minus 1 and everything that's larger, which is for instance g infinity, to 1, but everything else, everything that's smaller, to 0. Then we obtain this. H applied to g infinity minus 1 is 1, but h applied to gi is 0 for all I. Hence, h is not continuous. And this proves that the one-step consequence operator is not always continuous in a monotone setting. Which is why we need a continuous semantics, an explicitly continuous semantics, to make sure that, yes, our one-step consequence operator is in fact continuous, which guarantees that the least upper bound, the fixed point, can be found in countable time. Again, individuals interpreted in the same way, Booleans the same way. Function space now considers continuous functions. So the ones that preserve least upper bounds of directed sets. So the question you may have now, we have strayed very far from our original problem definition that used the standard semantics. How do these different semantics relate? Well, they are in fact equivalent, which means that if the original HoCHC problem is solvable under the standard interpretation, if the HoCHC problem is solvable under the standard interpretation, then it is also solvable under the monotone interpretation and the continuous interpretation. And there the implications work in all directions. Right, so what's the current state of the HoCHC project? Well, we do rely quite a lot on this continuous interpretation. For instance, in our solution methods, we have a Reynolds-style defunctionalization algorithm that's given a set of HoCHC clauses, reduces this in order by introducing closures, etc., all the way down to order 1, when it can actually be decided by regular constraint solvers. And this defunctionalization does rely on continuity as well. So do our resolution proof systems, of which we have 2. They are morally equivalent. But a big advantage of the resolution proof systems over the defunctionalization is that it's much more intuitive, much more user-friendly, because you're not introducing these closures with lots of indices and etc. It's fairly intuitive what's happening. And these resolution proofs are based on SLD resolution. So they are linear in some sense. Furthermore, we've been working on decidable fragments of HoCHC. HoCHC itself is semi-decidable at best. But of course, there may be interesting fragments of it that are fully decidable. And yes, it turns out to be the case. There's high-order data log, which is HoCHC with no higher-order tree constructors and only a finite set of individual constants. We have initial limit data log, which Toby Cathcart-Byrne, Luke Owen, Stephen Ramsey, Dominic Wagner will be presenting at LIX, I think, which is basically high-order data log, which is basically HoCHC extended with, it's high-order data log extended with individuals, but these individuals must be upward closed, as in a predicate must be closed with respect to upward closed with respect to individuals. So if we have a predicate over integers, for instance, if P of 5 holds, then P of 6 must hold as well, etc., etc. There's also some limitation on the types. And finally, we've been working on a monadic shallow linear fragment, because for some reason, this fragment keeps arising in first order verification in different settings with slightly different definitions. But essentially, if your heads are shallow and your variables are linear in the heads, your predicates are monadic, then you obtain a decidable fragment in first order logic. We've been trying to extend this to higher order logic. It's surprisingly more complicated, actually, because you may have variables that are higher order and need to be instantiated. And it's hard to do this without throwing off the order. So that sort of interferes with decidability termination, because you're not necessarily always making progress in a strict sense. Yeah, we have a whole logic that is remarkably similar to HoCHC. This is still in its early stages, but we're hoping for something more in the direction of using whole logic as a means rather than a goal. Maybe we'll be able to prove some general properties of HoCHC using this whole logic. And for the remainder of the talk, I want to dive a little bit into high-order model checking via HoCHC, which is something I've presented at the Horn-Klotz and the verification workshop. Right. So in the beginning, I mentioned that one of our motivations is the limitations of high-order model checking, for instance. But at the same time, we want to guarantee that HoCHC is still expressive enough to do what high-order model checking does as well. So one thing I've tried to do is solve the Hall's equivalence problem using HoCHC, and in particular co-inductive HoCHC. Yeah, Halls, which are the subject of high-order model checking, is a widely studied approach to high-order verification. And the decidability of the Hall's equivalence problem is open. It has been open for a very long time. It's recursively equivalent to the lambda y bone tree equivalence problem. These are basically trees, computation trees that allow lambda bindings within the tree. And there's one particular background theory that seems exceedingly suitable for this purpose, which is Ma's complete and decidable theory of trees, which includes infinite trees and finite trees. Right, so this is the reduction I'm aiming for. Given two high-order recursion schemes, I'll explain what they are in a bit. We construct two co-inductive HoCHC problems over this background of trees. Yeah, it consists of 3 stages. I'll not go into all of them. But yes, we will encode HoCHC into HoCHC logic programs and then define the two HoCHC instances. So what are HoCHC? HoCHC are essentially high-order tree grammars. So at order 1, they are just regular trees. At order 1, algebraic trees. Order 2, hyperalgebraic, etc., etc. Another way of thinking about them is as programs of a simply typed lambda y calculus with uninterpreted function symbols. And Hall's model checking is decidable over MSO, which is why it's been studied so frequently in high-order verification. Right, so the formal definition, we have a tuple, a set of non-terminal symbols, which are the productive ones, a set of tree constructors, terminal symbols, some rewrite rules, and a start symbol S. We assume determinism, which means that for every non-terminal symbol, there's exactly one rewrite rule. And a consequence of this is that the horse generates only a single tree. But this tree might be infinite. So again, we have sorts here, but now we only have an individual sort, which we interpret as trees. The set of all finite and infinite trees over our tree constructors, and bottom, where bottom is sort of an unfinished computation, non-termination or divergence, however you want to call it. And yeah, we have a partial order on these trees, which means that bottom is smaller than everything else, and hereditarily so. So if we replace a subtree by bottom, we get strictly smaller. So for instance here, if we replace this left subtree with something larger, the tree gets larger. Here, right subtree is instantiated, becomes larger. Again, getting larger when we replace this bottom by 0. So let's look at an example. This is in order 2 horse with 3 non-terminal symbols, 3 terminal symbols. So from the start symbol S2, we unfold once to get F suck. Then we unfold once again. We instantiate this phi with suck. So we get cons suck 0, which looks like this. And on the right-hand side, we have the interpretation of this tree, essentially. So all the leaves that are labeled with a non-terminal symbol as the head symbol become bottom in the interpretation. So we keep unfolding, keep going, until in the limit of this tree, the limit of these trees, actually, we obtain an infinite tree where each left subtree has 2 to the power n occurrences of suck. So 2 to the power 0, 2 to the power 1, 2 to the power 2, etc., etc. Right, so here we have the reduction outline again. Given 2 holes, we want to construct 2 HoCHC problems, co-inductive problems, which share their logic programs, but have different goal clauses. So I'll skip this first stage, which gets rid of bottom in the trees. Yeah. So part 2, encoding these holes into HoCHC. You may have already noted that these holes look very similar to HoCHC logic programs, except of course the types don't really match. Because yeah, holes only have trees, whereas HoCHC has individuals, which could be the trees, as well as booleans. We aim to define HoCHC such that when we interpret this R of S, which is a new predicate symbol corresponding to start symbol S, when we interpret this in the greatest fixed point, the greatest model, because remember, we're co-inductive now, so we're no longer interested in least models, but we are interested in greatest models. If this RS evaluates to 1, when applied to a tree T, then this tree T must be the tree generated by the holes, and vice versa. So essentially, we want to define this R of S to be the characteristic function of the holes G. And yeah, the background theory is this theory of finite and infinite trees, which is equational. So we can have 3 equalities, 3 inequalities, and it's complete and decidable. So for this encoding, we take a holes non-terminal and define a holes non-terminal F and define a relational variable R of F in the HoCHC program. And we lift the rewrite rule from the holes using these angular brackets. This gives us a strange logic program that's essentially, yeah, the holes in continuation passing style. So where the result is also passed as an argument to become a Boolean. So for instance here, the first order rewrite rule, S1 is I applied to G of 0, is mapped to this rewrite rule. So first of all, we have this lambda R, which is introducing an argument. Because yeah, S1 had no arguments, therefore R, S1, must have an argument, namely the result of S1. We have existential quantifiers for all the arguments. Essentially what we do, we take every subterm of this rewrite rule and turn it into one conjunct. So here, I applied to something becomes Ri, R1, which is the something, with the result R. And then this something is further constrained by this Rg of something is R1. And this something that is passed to Rg is 0, as we see here. So every subterm in the rewrite rule becomes a conjunct in the logic program. If we go to second order, it becomes a bit more complicated. So if we look at the first rule, we have f of suc, which looks very similar to what we had before. But now, because suc is higher order, we can't just pass it as itself, because suc has type iota to iota, I to I, which is not a valid type in the logic program, because it doesn't have a proposition at the end. So we have to first lift this suc to something that's acceptable relation sort, and then pass it to f. So you can see that here. We've hereditarily applied the lift to suc to say that, well, okay, we pass something to suc and we have a result. So here we can see the both constructions combined. Whenever an argument is of sort iota, it's that way. So for instance, here we have R3, which is just inlined. However, whenever a sort is of higher sort, then we lift hereditarily and just inline the hereditarily applied term. So here, R of f is some hereditarily lifted term, which is of course this b phi phi. But yeah, all you need to know really is that it's a sort of continuation passing style applied hereditarily in a systematic way. Right, yeah, that's an example. And finally, yeah, how do we get to useful co-inductive Hodge instances out of this once you've defined these logic programs? So let's say we have halls G1, G2, both deterministic, of course. Then we can construct Hodge-Gore formulas like this. The first one says, okay, there exist two trees, R1 and R2, that are accepted by the respective halls, and these trees are equal. The second one says there exist two trees that are accepted by the respective halls, and the trees are not equal. So recall that we have defined R to correspond precisely to the characteristic function of the tree generated by G1. So there exists precisely one R1 such that this formula is true. And same, of course, for R2. So what these Gore formulas are saying is the two halls generate the same tree and the two halls generate different trees, which is precisely what we need for the Hall's equivalence problem. So if we take the union of the logic programs we've constructed for halls G1 and G2, two co-inductive functions, then if the halls are equivalent, then P1, our first problem, must be solvable. And if they're inequivalent, then P0 must be solvable. So we've now reduced the Hall's equivalence problem to inductive Hodge. However, you may wonder, have we gotten anywhere with this? Yes, no, I would say. On the one hand, necessarily made the problem much easier. But on the other hand, we have reduced Hall's equivalence problem to something purely logical terms. A concrete answer. It has given us a bit more direction to perhaps prove that it is in fact undecidable. Because of course, co-inductive Hodge conjunctive first order horn clauses are generally not decidable. So it seems very unlikely that conjunctive HoCHC will be semi-decidable at all, which see this. I'll skip over that. I think it's a technical. Right. So the contributions of this section, Highorder model checking Firewatch, is of course, first of all, this conjunctive HoCHC framework. We have shown the actual way of interpreting these HoCHC clauses conjunctively, which is essentially taking backwards closure of the definite clauses. It enjoys greatest model property, etc. It behaves as you would expect it to behave. What I've not shown you is that we indeed eliminate non-termination from HoRs without meaningfully changing them, which is something that wasn't known up to now. We have shown that we can encode HoRs into HoCHC logic. And you might wonder, is this any use at all? We've reduced HoCHC, and we've just said that conjunctive HoCHC might not be. May be true, but at the same time, there's nothing much inherently conjunctive about encoding. As in, we could pretty much use this inductive HoCHC if you something, for instance, if you are interested in these over finite trees, prefix of trees, this will work just fine. So yeah, of course, we have reduced false equivalence to semi-decidability of co-inductive HoCHC. It was a problem. As for further directions, well, specifically about this aspect, Highorder model checking via HoCHC. Semi-decidability to be found. We are talking about a very restricted form of conjunctive HoCHC, namely decidable theory of trees and image encoding, which is also very limited clauses, really. So perhaps that, but I feel like it's more likely that we're going towards a proof of compatibility, false equivalence. And for the HoCHC project in general, I think we've mostly been working on decidable fragment settlement. And something we haven't done so far, because it seems a bit daunting, implementing a solver for HoCHC. So we do these two, but of course we implement them in such a way that because in general, the complexity isn't great, and you do rely on countability of the number of candidates, so that could be a massive blow-up. So what we're aiming for instead is focus on a decidable fragment, create a solver that's complete for this fragment, and accept that it will be, of course, incomplete for general HoCHC. But yes, we are focusing on a more a more dedicated solver than just for the resolution proof systems we've come up with so far. Something more specialized to some, which may be like linear fragment as well. So yeah, thanks for your attention. Any questions?